Our next speaker is someone I had the pleasure of meeting at FluentConf. I got to speak at O'Reilly has a conference in June, and it was really cool because I was feeling like really nervous. I didn't know anyone. I hadn't been to the States in a while, and just the week before FluentConf was JSConf Europe, and one of my friends, Manuela Castrillon, she got to go to JSConf, and I was talking to someone at Fluent, and I was like, oh yeah, my friend Manuela, and he was like, wait, you know Manuela? And I was like, you know Manuela? And like, we just hit it off. We were like, oh, hey. So this next speaker, super cool, works at Netflix, works on internal tooling, and this is an awesome talk. Don't know how useful it will be for work stuff, but Trent Willis is going to teach us how to make our own image formats in the browser. So everyone give Trent Willis a big hand.
Okay. Hola, JSConf. I'm so excited to be with you all today because I love the web and I love JavaScript. And what better place to celebrate that than with a bunch of other enthusiastic JavaScript developers? So I want to start this talk today by asking you a question. How many of you are familiar with Atwood's Law? Okay, only a few of you. Great, you get to learn at least one new thing today. So Atwood's Law comes from Jeff Atwood, who's better known online as Coding Horror. He has a blog. And about 11 years ago, he wrote a blog post that said this: any application that can be written in JavaScript will eventually be written in JavaScript. Now, at the time he wrote this, it was just kind of a funny observation. But over the last several years, this has proved remarkably true, right? As JavaScript has gotten more and more powerful, we see more and more things being written in JavaScript. And that's one of the things I really love about the JavaScript community, because we do so many awesome projects. We now use JavaScript as the primary language for our chat clients, for our music players, and even for our development environments. But not only that, we can recreate old school applications that people love, like Winamp, and do it all in the browser now. We can also build progressive web applications that have offline capabilities and push notifications and other native-like features. But even more than that, we can even re-implement runtimes for other languages like Java and Ruby in JavaScript. And that's incredible to me. Who would have ever thought that that is where we would be, even just a couple years ago? So today, I want to talk about something that I feel is also in that same vein, and that is how we can now create our own image format in the browser that behaves just like it was a native part of the browser. Now, compared to some of the things I just mentioned, this may not seem like that big of a deal. But I actually think it is, because up until recently, if you wanted to support a custom image format or a custom encoding for your images, you would have to do a lot of hacky things. But because the web platform has evolved so much and become more extensible and powerful, we can now do this without jumping through a lot of hoops. So while I think this topic is pretty cool in its own right, it's also going to serve as a great way for us to learn about and see some of the new APIs that are available to us on the web platform. But before we jump into all that, who am I? So my name is Trent Willis, and currently I work at Netflix as a senior UI engineer. But more importantly, today I'm here as someone that's a lover of the web and a lover of JavaScript, because JavaScript is continuing to evolve, and there's a lot of creativity and excitement to be found there. And there are so many opportunities for us to experiment with new things. And that's really what spurred this whole talk. I found an interesting bit of information about what the web platform is capable of doing, and I decided to run with it. And next thing you know, I'm here and talking to you all. So what is that interesting piece of information? Well, earlier in the year, I was reading a specification published by the Web Hypertext Application Technology Working Group, better known as WHATWIG, because that full name is way too long. And I was reading their specification for streams, which aims to provide a set of APIs to allow web developers to interact and easily consume streaming data. This is pretty common in the Node.js world, where streams are a built-in feature. But up until recently, it wasn't something that we had a primitive for on the web platform. But what was interesting is that in the introduction of this spec, one of the potential use cases they identify is that if a stream is installed inside the fetch hook of a service worker, this would allow developers to transparently polyfill new image formats. And this got me thinking, that's pretty awesome. I had never really considered using service workers for things other than traditional progressive web application functionality. And I got even more excited as I thought about this, right? Because images are such a huge part of the web. From funny cat pictures to important news photos, they're a large part of how we consume and relate to the content that we see online. I would go so far as to say without images and videos, the web is honestly kind of boring. So wouldn't it be awesome if we could actually experiment with this critical part of the web, try out new image formats, and innovate in that space? I think so. It also opens up a whole new area for us to just be creative in and try things out and pursue artistic endeavors that we might not otherwise be able to. But being a pragmatic person, I also tried to think of a scenario where this would actually be useful to some folks in the real world. And as I thought about that, I discovered another web API that I wasn't very familiar with. That is the Web Crypto API, which defines methods that allow you to encrypt and decrypt and sign and verify data using various cryptographic algorithms. And I thought to myself, hey, that's pretty cool too. How could I use both of these APIs in a single project? So my thought was, well, why not build an encrypted image format that could restrict who's able to actually see the images you're sharing? In a privacy-conscious world, this seems like something that could have some practical applications. And so that's what I did. And I decided to call this little project Cryptogram, because Instagram is a thing that exists, and I'm not very good at naming. And that's what we're going to talk about for the bulk of the rest of this talk, about how we are going to implement this. And along the way, we're going to learn some cool things about service workers and streams and web cryptography. So let's dive in. We're going to start with thinking about what we're building before getting right to the code. If we have an encrypted image, which is, for the sake of this talk, just a PNG image that we ran through an encryption algorithm, we want to be able to display it to our users by just using a normal image element. But we know that currently this won't actually work in the browser because image elements only display PNGs or JPEGs or GIFs or other image formats that the browser already understands. So that means what we really want to focus on is how do we get that encrypted image to tell the browser that it's actually a PNG image so it renders correctly. And the answer to this is use a service worker. Many of us are familiar with or have heard of service workers as a means of progressive web app functionality. But what we may not think of them as is they're actually just a proxy that sits between our applications and our servers or our CDNs. And so when we think of them in this light, as a middleman for our requests, essentially, it becomes relatively obvious how we could load an encrypted image but display a decrypted one to our users. So how this will work is we will fetch a .epng or an encrypted PNG file. We can transform it in the service worker and then display it as a PNG file to the browser. And the browser will be none the wiser and will render it as it should. So that's the high-level idea. But how can we actually do this? Well, there are two APIs that we need to be familiar with in the service worker to make this happen. The first is known as a fetch event. So this is pretty much the core and most critical part of most service workers. And it is an event that's fired any time a request for data or a file is made from a domain where a service worker is active. And so this isn't just for JavaScript-initiated things like XHR requests, but even for things like image assets or your JavaScript files. And the event contains a whole lot of information about what is going on in this request, such as its URL. But this doesn't really get us where we want to be. We don't just want to see the requests and know what's in them. We want to replace them with something. And so we need a second method, which is the respond with method. And so this is a method that's actually on the fetch event object every time you receive it. And it basically says, hey, you're fetching this request, but instead of responding with the normal network payload, respond with this thing that I'm giving you instead. And this is how we build offline apps, right? When we get a request, we get a fetch event, we can say, hey, instead of responding with this data that you got from the network, respond with this data that we already had stored in a cache. And this is the core of how that works. So with those 2 bits of knowledge in hand, let's go write some code. One last warning. All code is going to be available online, so don't worry about all the nitty-gritty details. There's going to be a lot of code shown, but it's really more important to just focus on the high-level ideas and how we kind of wire everything up. So let's get to it. We're going to start by registering a service worker. I like to be obvious with my naming, so I name my service worker files service-worker.js. Pretty obvious. Now, in that file, we want to define an event listener for the fetch events, which is pretty standard to how you normally add events using vanilla JavaScript. Now, by default, this function won't do anything to our request. If we don't do anything with it, then the browser will behave as normal. And so that's what we want to do for the majority of requests that our app sees. However, if we get a request for an encrypted image, then we want to do something else. In this case, I'm using a function for this if check because sometimes these checks can get kind of complicated, but more importantly, I think it makes the code more readable. And so our check in this case is just going to be to take the request, get the request URL, and make sure it's ending with a .epng file extension. Now, this isn't a super robust implementation, so I wouldn't recommend doing this in production, but it works for our use case. So if we have an encrypted image request, what do we want to do with it? Well, we want to take the event and tell it to respond with a PNG that we generate from the encrypted image request. So remember how I said I like descriptive names? That's definitely the case here. And sometimes this gets a little verbose and wordy, but it will help whoever comes along after you and tries to understand your code. Now, this is actually the majority of the service worker-specific code that we need. Everything else that we're going to look at is really just JavaScript that you could do on the main thread or in a service worker or another worker. So let's talk about the image processing code. How do we actually generate that PNG from an encrypted image request? So in order to do this, we need to do a couple things. First, we fetch the actual request. And we use this using the normal fetch API that you would be familiar with even on your normal application code. And then once we have that response, we turn it into an array buffer. So many of you may be familiar with a response.json method. In this case, we're getting the data as an array buffer. And this is because when you're dealing with images, you often want to deal with an array buffer or an array of integers instead of strings or textual or objects because it's just a better representation for image data. And I think we'll probably hear more about that in a couple talks from now when we learn some linear algebra and how it applies to image processing. So anyways, with that data in hand, our encrypted data, we can pass it to a decrypt data method, which we're going to write in a little bit, and then take that decrypted data and create a blob from it with an encoding of image/PNG. And so this is important because there are only a few types of objects that responses from a service worker can understand. And so blob is one of those formats, and it allows us to encode it as a specific type, in our case, a PNG image. And then finally, we can turn that into an actual response object, and we return that to our respond with method, and voila, we have a working encryption or decryption method. So now there's a good bit of interesting code here, but really it's just these 2 lines that we need to focus on. Because where we get the encrypted data, get the array buffer of data, and then decrypt it is where most of the magic happens. Because that's actually how we implement our custom image format. In fact, we could change a few things in this function and make this very generic, such that if you passed in any transform function that took in data and responded with a PNG set of data, you could actually plug it in here. So how do we actually decrypt this data? Now, earlier I mentioned the Web Crypto API, and it's at the core of our image format here. And again, there are 2 primary APIs we're interested in, so we're going to look at those before writing the actual code for it. The first is known as subtle crypto, and so this is the global object that you'll actually interact with. It's available in most browsers as crypto.subtle, and it's basically just a namespace. And it provides a set of cryptographic primitives, such as methods like encrypt and decrypt, or generate key or import key. And it's named subtle crypto to reflect the fact that many of the algorithms it exposes have subtle usage requirements in order to provide the required algorithmic security guarantees. Basically, cryptography is a really fascinating area of computer science, but it's also really complex. And it has some nuances to it that you need to understand if you're going to use it as part of your application's security measures. In our demo, though, we're really more concerned with the general concept, so I'm not going to dive into those too much. There are plenty of wonderful security-focused talks online that you could go check out if you're curious. So the second API that we need to be familiar with is the crypto key API, which, as you might guess, is an API to represent keys for our cryptographic methods. Every method in the Settle Crypto API requires one of these keys in order to function. And so, for us to decrypt our images, we're going to need one as well. So with those two ideas in our mind, let's put them together in the actual code. If we go back to our function, we can start to implement our decrypt data method. We'll start by receiving the encrypted data as an argument to this function, and then we'll get our crypto key. Now, I'm not going to dive into this function a whole lot because it's kind of boring and not that relevant to what we're doing. The important thing to note is that the key value that we get back is a crypto key object, and it has to be the same one that we used to originally encrypt the image. Next, we want to define our decryption options. In this case, we're specifying an algorithm that we're using, which is the AES encryption algorithm in what's known as CTR or counter mode. And I'll go into the details of that a little more in a bit. We also want to provide a counter, which is going to help us count how many blocks of data have been decrypted, and a length. And the length specifies how big the blocks of data are that we're decrypting. Again, I'll cover more in-depth those problems in a little bit, but for now, just know that they're required in order for us to actually decrypt this data because it's what was used to encrypt it. And so finally, we use the crypto.settle.decrypt method and pass it our options, our key, and our data, and return it. This will return us a promise, which will resolve with the decrypted data. But thankfully, since we can use async await, it's much more readable than having to do a bunch of .thens. And so with that in place, that's actually all the code that we need in order for this to work. So let's take a look at a demo. In this demo, we start with the service worker disabled. And so you get Chrome's lovely broken image icon. However, if we go in to our network tab and don't disable the service worker, actually let it go through there and load, voila! It works. So you can find this demo online at cryptogram-naive.glitch.me. So definitely check it out sometime because there are a lot more nuances that I didn't cover in this talk just because I don't have enough time, but I heavily commented the source code there, so you can check it out. So now that we have that working, let's focus on optimizing it a bit more. Right, the three tenets of good software design are to first make it work, then make it right, and then make it fast. At this point, our Polyfill works, and it's producing the right results and is doing everything that we want it to, but it's not necessarily fast. And the reason for that is because before it can actually begin decrypting the image, we have to download all the encrypted data. And for small images, this is fine because you don't really notice. But for larger images, this can mean that we're wasting a lot of time because we're waiting for all this data to download, and then we're doing all the processing. And this also means that we have to hold all that data in memory twice. Once for all the encrypted data, and then again as we're decrypting all of it. So this is known as batch processing, because we're basically waiting for all the data to arrive before processing it in one large batch. So how do we make this better and faster? Well, we do it by changing our approach, and instead of batch processing, we process the data as it arrives, or process it as a stream. We can do this using the Streams API I mentioned at the beginning of this talk. Now, if you're not familiar with stream processing, you might wonder how this helps, because we still have to do the same amount of work on the same amount of data. So let's walk through the idea here. Like before, we begin by downloading a chunk of data. But after a little bit of that data has downloaded, we can actually begin decrypting that. And as that decryption is happening, we can download more data. And we just repeat this process until we're finished. And so what happens is that this becomes faster because instead of waiting until all the data has downloaded, we can actually do some of the work while the data is downloading. And so the end result is that we're not necessarily going to be as fast as not having to do any work, but it'll be much faster than doing it in a batch processing model. So that's the idea. Let's implement it. If we jump back to our polyfill function, we can start by changing a couple lines here. so that instead of returning a PNG blob, we're actually returning a PNG stream. Let's walk through this code. So as before, we start by requesting the encrypted data. But then we want to construct a transform stream object that's taking as its argument a decrypter object, which we'll implement in a moment. We can then take the response body from our fetch request and pipe it through that transform stream. Now, many of you probably aren't familiar with the body property on a response object, but it is actually a readable stream of data that allows you to access the data from your request as it arrives over time. In this case, we're simply using a pipe through method which says, hey, every time you get some data, run it through this function. We can then take that stream and create a new response from it. So that's the gist of what needs to happen. But let's dive into this whole transform stream business and the decryptor stuff, because it's kind of complicated, and that's where the interesting things are happening. So the Streams API has two primary constructs we need to be familiar with. Writable streams, which, as the name suggests, are streams that you can write data to so that they can be consumed or processed elsewhere. This is essentially what your server does anytime it sends data down to the client. It opens a stream and sends data down through it. The second construct is a readable stream, which, as you might guess, is the opposite. It allows you to read data from a stream, and it represents a set of data that you can access over time. And this is what the response.body object is. So what is a transform stream then if these are the two core constructs? A transform stream is actually just a writable stream plus a readable stream that have been wired up together with a function in the middle. The idea is that you get some data input into the writable side of it, you process it in some fashion, and then you put it into the readable stream for someone else to consume later. So you could actually construct a transform stream object with these two other objects yourself and handle all the wiring up manually, but it's actually a lot easier if you use the transform stream constructor with a transformer object, which is really just an object that allows you to focus on the transformation aspects and not wiring up and putting in this boilerplate code. So this interface specifies three methods: start, transform, and flush. The start method, as you might guess, occurs whenever a stream starts to receive data, and you can do initial setup and setting up some state there. The transform method is where the actual transformation takes place, and this is where we'll spend the bulk of our code later. It receives chunks of data that you can operate on and then enqueue them into the stream's output. And then finally, flush occurs once the stream is done sending data and about to close. Here you can do cleanup and final processing that might need to occur. So let's say this in action, because that's a lot of words, and code makes it a lot more clear. So if we look at our decrypter object, which is actually a class that has three methods on it: a start, transform, and flush. Now, thankfully, the streams folks were very smart and decided to make these support promises as a first-class primitive. And so that means that we can actually make them async methods, which is going to make our code a lot more clean and readable. So in our start method, we want to set up a counter. This is the same type of counter we used previously, and it's going to let us count the number of blocks of data that we've decrypted. So since we're streaming it, we need to increment this counter so we know how much we've decrypted so that the algorithm continues to work. And so that's what the counter mode in the AES-CTR counter meant earlier, is that it's going to actually enable us to do this in a streaming fashion. Otherwise, you would have to decrypt it all in one giant batch. Next, we want to get our key, same as before, and the key is going to be the same every single time we run the transform, and so we don't need to get it more than once. Now that we have that state set up, we can dive into the transform function. So this is a lot of code, but we'll walk through it, and there will be even more code. But basically, we start by getting a chunk of data and a controller object. The controller object is what allows us to then write the data out. We get the length of the data and take that length divided by 16 to get our blocks. And this is because we specified earlier a length of 128 bits for each block in our encryption. And so 128 bits translates to 16 bytes, and thus we divide it by 16. And that'll give us the number of blocks that's in this chunk of data that we just got back. We can then decrypt the data using a slightly modified version of our function from earlier, where we pass it our key, our data, and the counter. And then finally, we enqueue that data into the output or the controller. And then we'll need to increment our counter. And this is just an annoying piece of housekeeping that you have to do because the counter isn't incremented by the subtle decrypt method. It's mainly just used as a starting point. It tells the algorithm, hey, start decrypting from this block. Now, the observant among you might have realized that, hey, what if we get data that's length isn't an exact multiple of 16? Well, to handle this, we have to write some more code. First, we start by taking the modulus of the length by 16, and that'll give us the remainder, or how much data we have left over that didn't fit into a block. We'll then slice off that data and save it into a stateful variable called remainder data, and save it for the next run of the function, where we can then concat that with a new chunk of data at the beginning and proceed processing as normal. So basically, what all this is doing is until the stream finishes, we need to make sure that we're only operating on complete blocks of data so that we can properly increment the counter and track it over time. So if we collapse this function, because it's pretty long, and move back, we have one function left, and that is our flush function, which, similar to the transform function, gets a controller, but doesn't get a chunk of data. Here, we're just going to see, hey, do we have any leftover data from our transform function? And if we do, we decrypt it and then enqueue it. And at this point, we don't care if it's a full block of data because we're done with the stream. Cool. So here's a similar demo to the one we saw earlier where we start with a broken image. But as we enable the service worker, we can see the data getting streamed down and processed. Now this is drastically slowed down. I put in a set timeout just to emphasize the fact that the data is arriving over time. But if we remove that artificial slowdown, you can see that the image actually gets processed pretty fast. And this is a large image. And so this is exciting to me because it means that we can build efficient transforms that actually get put in a way that developers don't really need to know that they're there because it's all being done in the service worker. They write their code the same way as before, but the transformation still gets applied. So we just covered a lot of code. And you can find it all online at cryptogram-streaming.glitch.me. And this would actually be a lot simpler if the crypto API actually just supported streaming natively. And there's actually an open issue on GitHub for that to happen, so that might happen in the future, in which case these demos will become really easy to do. But the specific details of that code is not really the point of this talk. I think it's interesting, and I hope some of you all found it interesting or at least learned something from it. The real point of this talk is to showcase how we have so many new, awesome primitives for building things on the web platform. Service workers, web crypto streams, these are just some of the cool things that we can now do on the web that were not previously possible. So to end this talk, let's talk about some of the other things that we might be able to leverage and mix in with these ideas to build more awesome things on the web. Let's start by talking about some WebAssembly. If you use WebAssembly to get really fast algorithmic processing, which is something WebAssembly is really well suited for on the web, you could create lightning-fast data transformations that you could use with streams. And you could compose them, because streams you can just pipe from one to the next, one transform to the next. You could build encryption protocols that aren't part of the Web Crypto API, or create any sort of processing that you might need for your data to happen before it actually makes it to your client. So there's a brief demo of how this might work at wasm-streams.glitch.me. You can go check that out after the talk. Or what if we took the ability to intercept requests and change how we think about our development processes? Right? What if you didn't have to have a local build step for your TypeScript or your Babel project? Because you could do it at runtime in the browser instead, and it would just cache the results. And then if the file doesn't change, it just pulls it out of cache the next time. Now, I'm not familiar enough with Babel or TypeScript to know if this is feasible, but it would be awesome. Not having to boot up an environment every single time you want to work on just a client app sounds wonderful to me. Or maybe you could completely polyfill extensions to the web platform. Like, what if you could import HTML files into your ES modules and use them inside your JavaScript? I put together a small demo of something that I would like to see happen, which is an HTML modules polyfill that allows you to use HTML templates in your JavaScript code using normal import statements. And while we're talking about ES modules, what if you could actually experiment with being able to import assets by name instead of file path in the browser? There's a proposal for this known as package name maps, and I put together a small, roughly working polyfill called packagenamemaps.glitch.me. And it works. It's possible with a few caveats. But this is great because it allows folks to begin experimenting with new proposed standards, even when they may not necessarily be ready to ship. Or finally, what about inserting video effects at runtime in the browser? This could be possible with streams. Right? You get streaming video data, you put in some transforms, and all of a sudden, you can process and change those videos in real time as folks are watching and interacting with it. Now, unfortunately, I didn't have time to make a demo for that one, but I probably will in the future because it seems really cool. And so these are just a few ideas I've been mulling over the last few months. So while today I talked about how we can create our own custom image formats specifically, I really want you to walk out of here knowing that there are so many new and powerful tools that we have available to us on the web platform that you can use to fuel your creativity in new ways. Right? Whether it's service workers, streams, new ECMAScript standards, or web components, they're all setting the stage for us to build more ambitious projects than we ever have before on the web. And I'm very excited about that, and that's why I love coming to conferences like this. So I'd love to see what you've built and what you're going to build in the future. So go forth, make Atwood proud, and write everything in JavaScript. Thank you.